Okay, go for it.
Okay, good evening, everyone. Our speaker tonight is Dr. Allison Strom from Princeton University, Department of Astrophysical Science. She enjoys conducting public outreach and is active in the Women Mentoring Women program. Her research focuses on the chemical enrichment of distant galaxies. Her presentation is the DNA of galaxies. We welcome Dr. Strom.
Well, thank you for having me. I always like these opportunities because it's an opportunity for me to remember that science is not just about calculations and facts, but also about storytelling. And with astronomy, we're very privileged to have a story that is relevant for everyone. Astronomy is the story of the universe, which means it's part of my story, it's part of your story. It's something that connects us all. But to start at the beginning of the particular bit that I'm going to talk about today, I want to raise the question to all of you about what is a galaxy. It's important to be on the same page if we're going to spend some time together talking about that. And when I say the word galaxy, I'm sure that everyone has a different idea. You might think about one of these galaxies that you see in the zoom through of the Hubble Deep Field. You might think about Andromeda. You might think about the Milky Way. And the Milky Way is actually the best place to start when answering the question, what is a galaxy? So I just moved to New Jersey from California, from LA specifically, and oftentimes I would ask people if they'd ever seen the Milky Way when I would give public talks. And unfortunately, a lot of people said no, which is maybe not surprising if you've ever visited LA and seen the light pollution. But if you have been fortunate enough to see the Milky Way, our own galaxy, when you go out on a dark night, it looks something like this beautiful picture. You can see, of course, all of the individual stars that are in other parts of the galaxy, but the Milky Way is this band of much higher density of stars. You see the dust lanes. This is a particular picture where you can see sort of red areas around young stars. And it's really magnificent. But I can imagine, because it is so singular, that when people early on in human history first saw the Milky Way, they must have had a lot of questions. I think a lot of people today have a lot of questions when they see the Milky Way. You know, how many stars are there? How big is it? Where are we in the Milky Way? How did it end up like this? And all of those questions require learning not only about the Milky Way, but also about other galaxies. There's been a lot of theories, and I will start with one that I actually like a lot, which is a story from the Cherokee, which involves people who lived in the South and depended on corn for sustenance. And so every day they would spend time milling corn into meal at their corn mill. And that was how sort of their days proceeded. But after a while, they started noticing that when they would go to the mill in the morning to fill it, that some of the meal would be gone. And what they noticed were dog paw prints sort of in the dust around the mill. And so the next night, the entire village hid around the corn mill with drums and with rattles. And when the dog, which was the spirit dog, came to take this cornmeal to feed itself, to steal from the people, they made a bunch of noise and sort of chased the dog off, who then ran to the north, dribbling cornmeal as he went. And that is how the Cherokee explained the origin of the Milky Way. And the word that they use for that is actually the way the dog went. Other myths that I think people might be more familiar with, sort of from the Greco-Roman tradition, involve Zeus taking his mortal or half-mortal son and suckling him at the breast of his, immortal wife, Hera. And when she woke because she had not consented to this, she thrusts the babe away and spills some of her milk. And that is then what creates the Milky Way. And not only in the name that we call it, the Milky Way, but also the origin and the etymology of the word galaxy are related to the Greek word for milk. So when we look up galaxy in a dictionary today, though we don't see reference to these myths, instead we see a pretty straightforward, dry description. Any of the very large groups of stars and associated matter that are found throughout the universe. And if we think about how this applies to the Milky Way, you'll find that it's quite accurate. There's a lot of stars, there's a lot of matter, but for most of human history, both recorded and unrecorded, galaxy only referred to the Milky Way. In fact, it was only in the 1920s that we began to understand that there was more beyond the Milky Way. And the sort of linchpin to understanding this, to discovering that there was more in the universe, was our closest galactic neighbor, Andromeda. So in this picture, it's this sort of smudge to the left of the Milky Way. And even if you've seen the Milky Way, you may not have seen Andromeda. It's very challenging to see with the naked eye. In fact, a lot of people can only see it out of the corner of their eye because of the difference between rods and cones and the difference between color sensitivity and light sensitivity. But people had seen things like Andromeda. Astronomers had seen things like Andromeda, these smudges that looked very different from stars and planets. And there was a debate about where they were. Determining distances in space is extremely difficult and was extremely difficult then as well. And so we didn't really know how far away these objects were. And in fact, in April 1920, there was a debate between two famous astronomers of the time, Harlow Shapley and, oh God, what was Curtis's first name? I don't remember, but the Curtis Shapley debate, where they argued about the size of the Milky Way and try to, logic their way through whether or not these other objects were contained within the Milky Way, making the Milky Way the entire universe, or whether or not there was more to be explored. And the man who helped settle this debate was Dr. Edwin Hubble, who was working at Carnegie Observatories in Pasadena, so where I just came from. And he was looking at Andromeda using a methodology that had been refined by a woman, a computer, because women were not allowed to be astronomers at the time, named Henrietta Swan Leavitt. So Henrietta Swan Leavitt had found that stars of a certain class get dimmer and brighter and dimmer and brighter, and that this was how quickly they did this was related to how bright they were. So if you could see that pattern of dimming and brightening, you knew how bright the object should be, which meant that when you saw it someplace in the sky, you could then calculate the distance, the same way you might if you knew how much light a light bulb was giving off and you measured how much light you were seeing from it at a certain distance. So this is a photograph of a photographic plate, so I guess a scan of a photographic plate from Hubble's analysis of Andromeda. And what he was largely looking for were novae. And novae, meaning new, were things that would suddenly sort of become very bright and then go away. And you can see that he's marked a few, sort of N here, and then you see this N up here. But what he found, because he would take repeated images so that he could compare them to see which objects were brightening and then disappearing, he saw that this one got faint but came back again. So it was a variable star. It wasn't just a novae, it was a variable star. And that's why he crossed it out and wrote VAR. And it turned out to be one of these special kinds of stars that Henrietta Swan Leavitt had been studying. And so using the tools that she had provided, he determined that the Andromeda galaxy was, I'm trying to remember what he put in his paper, I think 1 million light years away, which was far, much more distant than any supposed size of the Milky Way. And so the community was forced to conclude that these island universes were in fact other galaxies that we could then continue to study. And I feel a special connection to Dr. Hubble in many ways. One of the first research projects I did as an astronomer was actually looking for novae in Andromeda, or M31, as you might hear some people call it. And I, as an extragalactic astronomer, am indebted to this discovery, because this was the birth of extragalactic astronomy, the birth of understanding things outside of the Milky Way. So we are very fortunate today that our ability to study galaxies like Andromeda is far beyond, I think, what anyone in Hubble's time could have imagined. So you'll see that this image is far more detailed than the photographic plate I showed you. You can now see from an outside perspective the same kinds of dust lanes that we see in the Milky Way. You can see the young stars with the sort of reddish gas around them, and the sort of change in structure and color as you move around the galaxy. And, you know, just as we talk about it being hard, you know, to see the forest for the trees, the same thing is true when we're trying to understand the Milky Way. It's much easier to think about the history of the Milky Way if we can look at a similar object from a different perspective from outside of it. Now, today, today we don't just know about the galaxies very close to us, but we know about the billions and billions of galaxies that have been imaged with things like the Hubble Space Telescope. So this is in fact one image from the Hubble Space Telescope, and you'll see that there's a huge diversity of galaxies, and many of them look nothing like Andromeda or the Milky Way, which we also know to be a spiral galaxy. You'll see some kinds of spirals, but you also see these sort of large yellowish footballs. You'll see mergers. And all of these, basically every point in this image is a galaxy. And I think that can be overwhelming. I think back to when I first started in astronomy, and you're trying to learn to ask good questions and learn how to ask questions that will teach you about the universe. But when confronted with this, you know, where do you even start? And so what I would like to do is pause briefly and step away from astronomy and have a Gedanken experiment. I'd like you to imagine with me that you are an alien visiting Earth, and you see all of these humans, billions of humans. You see them going about their daily life. You see them in large concentrations, small concentrations, and you really want to understand more about human development. This is similar to the problem that we have in trying to understand how galaxies develop. And the first thing that scientists do sort of across discipline when trying to understand new topics is put things into categories. So one might imagine grouping people by hair color. You can see sort of dark hair, white hair, blonde hair, no hair. I think there's a balder man over here. You could instead maybe do it by hair length. So a lot of people in this picture have short hair, but you'll also see some with long hair, or maybe by glasses or other sort of accessories. We see phones, we see regular glasses, we see sunglasses, hats, or maybe something like height, which, you know, we know from prior experience is actually correlated with something to do with human development. But you could imagine not knowing this in advance, you might choose something like hair color. And if you put all of the blonde people in one bin and all of the black-haired people in another bin and red-haired people and brown-haired people, and you tried to understand how this division would tell you about how humans sort of as a group evolved, you would find yourself coming up with some pretty far-fetched ideas trying to link these groups to one another, because in fact, they're completely separate. That aspect of a human has nothing to do with their development. But with height, things are a bit easier. So you can imagine taking all of the small people and putting them in a bin, and taking all of the tall people and putting them in a different bin, and sort of segregating humans according to their height. And then you want to then understand the connection between these categories. But if you're an alien, you don't really know what's going on. And so you might say, well, maybe you start off with a lot of mass, and then as you age, you use that mass up and you end up looking like this. You're very simple looking, you're very small. You've basically used up everything that the universe gave you to begin with. But we know that this isn't true. It's the opposite, that babies grow into children, to young adults, and into adults. But we only know this because of our prior knowledge. And the problem with hypotheses based on categorization schema like this, is sometimes they will fail when you try to apply them to samples that are different from the sample that you use to develop your theory. And so if we take this idea that tall people are always older than short people, and we try to apply it to specific cases, you'll see that it doesn't always work. So this is a picture of me with another human. And if we were in person, I would ask all of you to guess whether or not this other human were younger than me. She's clearly smaller than me. But I will spoil the answer. This is my grandmother, who is in her 80s, and indeed significantly older and wiser than I am. But this is just part of the population variance that becomes problematic when you use a correlation like that to try and understand in detail what is going on. So you can see how this works if you look at how human height and human age are actually related. So the CDC average for women goes something like this, where you grow very quickly at young ages, you continue growing monotonically through childhood and young adulthood, and then you plateau as you reach your adult height. But every individual will have their own path. They might be taller, they might be shorter, that you could imagine someone growing very quickly and then sort of tapering off and being relatively short. And so if you look at a single human height, you're actually looking at a variety of ages. And so using height as a proxy for age will complicate your understanding of human development. So the same issue affects us when we try and understand and categorize galaxies. The equivalent categories for galaxies might be something like size or color, maybe shape. As we talked about, there's a wide variety of shapes, or maybe exactly how that shape looks. So do they have very tightly wound spiral arms? Do they have loose spiral arms? Do they have no spiral arms? And it's actually something like this last one that Hubble himself tried. And you might be familiar with the idea of the Hubble tuning fork, where he sort of ordered galaxies according to their shape, or as we refer to it in astronomy, morphology, and called these early type galaxies and these late type galaxies. And you can imagine from this nomenclature that someone reading about Dr. Hubble's research might have believed that these were younger galaxies and these were older galaxies. And you could imagine thinking, well, we often think of complexity arising with time. So these are very simple, these are more complex. Perhaps that is how galaxies change over time. But if you look at the paper where he describes the galaxy sequence, he says that any interpretation or any attempt to interpret it as a sequence should be avoided. And so even he was a little bit suspect about interpreting this directly as a timeline for galaxy evolution. So what are we left with? We want to understand how individuals galaxies grow and evolve so we can understand things like the Milky Way. We want to understand how galaxies relate to one another. But this information that we have been considering is not enough. So I want to come back to our earlier thought about human history. And this is a picture of me with my other grandmother, which we know because we have lived together in the same time. But if we want to understand our collective history, her history and my history, we might be interested in looking even further back. So this is my great-grandmother, Thelma Pope Adams, and knowing for sure that this is my ancestor and we are her descendants. And we know this today because of record keeping and because of the stories that my grandmother has carried with her. But unfortunately, we don't have the opportunity to interview galaxies. But one other way that you might be able to link my ancestor to me and to my grandmother, to link all three of us together, in fact, would be to do a DNA test. And you would find that we have genetic similarities that indicate a familial relation. And so not only does someone's genes explain often how they develop, but it also allows you to link them between other people. And we can use a similar strategy thinking about galaxies. So we can't interview them, but we can test their DNA. And I'm going to spend the rest of the talk talking about how we do that. So the technique that we use to test galaxies' DNA is spectroscopy. So in the image that I showed before, and I think most data that people see in public releases about astronomy, you're looking at how light is distributed on the sky. So you're looking at this panel on the left. And yet there's a whole lot of other information that is also contained in the light that is arriving at our detectors, at our telescope, at our eyes. And that's what we call, a spectrum. So you're dividing out the light now by wavelengths. And when I was a college student, heard an older astronomer say, well, if a picture is worth 1,000 words, then a spectrum is worth 1,000 pictures, which means it's worth 1,000,000 words. And that has stuck with me, 10 to 15 years later. And I think it's a really good way of thinking about why spectroscopy is so important to astronomers, not only people doing the kind of work that I do, but a sort of across subject matter. So spectroscopy works by dividing a light source into its constituent wavelengths. So this is sort of a cartoon of white light hitting a prism, which you may have seen, and coming out as a rainbow on the other side. And this is occurring because light travels, light of different wavelengths travels at different speeds when not in a vacuum, depending on the index of refraction of the material. So as it's traveling through the prism, you can kind of even see it here, the light is moving at different speeds, and you end up also with this angle. So you have one interface, you have a second interface, and now you've spread this out into a spectrum with wavelength going from purple to red. And this is just a way that we talk about essentially what kind of light we're referring to. But to give you a context for where this sits with other radiation, infrared would be beyond what we can see in the red. So this is what is emitted by, often what we think of is emitted by warm bodies. And in fact, this was discovered by someone who put a thermometer just to the red of a prism dispersed spectrum and saw that the temperature increased relative to a thermometer left outside of the path of the spectrum. And on the other side, we have ultraviolet. So, things that bees can see, but not humans. So if wavelength goes from purple to red, energy, which is another way that we can talk about light, goes in the opposite direction, where red light tends to be lower energy or is always lower energy, and purple light and ultraviolet light is higher energy. But in the real world, we don't actually see these perfect rainbows very often. And that's because the light sources that are generating light are complex. So this is actually a solar spectrum that is spread out much more than you could do with a prism. And instead of just seeing all of the light from the sun, you see also these dark patches where the light is missing. And as it turns out, those dark patches arise because of material in the atmosphere of the sun that is absorbing the light at that specific wavelength or at that specific energy. And as a result, we can learn about what elements are present in the sun. And that's because every element has its own unique genetic pattern. It has its own pattern of emission and absorption. So the same wavelengths that an atom will absorb in, it will also emit in. So this is sort of just the inverse of what I was showing on the previous slide. And so this is just the periodic table: hydrogen, helium, lithium, and this is oxygen here, which I can always tell, not only because of its position in the periodic table, but also because of this bright green line. We know that oxygen is often seen very much sort of in green light. But if we look for these patterns in things like the solar spectrum, we are able to identify the presence of things like calcium, magnesium, iron. And in fact, helium was first discovered in the sun, not on the Earth, by looking for spectral characteristics like this. Okay, a more familiar example of the way that elements might emit and be perceived as different colors is the idea of neon lights, with neon, being the, Kleenex, the sort of generic word for the kind of light that excites this gas, ionizes the gas, and then you see the color coming from that gas. So if I were to show you a lamp that had just hydrogen gas, and we sort of heated it up using an electric current, it would look kind of pink. And the reason for this is because it's actually spread out into these discrete lines, with the brightest line being this long wavelength red line, but also sort of a cluster of fainter lines in blue and purple. And so you end up with sort of a weighted average being this sort of purple color. And this is the same way that all of the atomic spectra were displayed on the periodic table. But when we're interested in measuring this information, we actually look at how bright each of these lines is as a function of wavelength, and we refer to this as flux. And you can basically record this information and use that to study the hydrogen emission. And so this is essentially what we are doing when we're taking a spectrum of an object. We are looking at how it's dispersed, but also looking at how much light is coming out at each wavelength. Now, there aren't neon lights in space, but we have the next best thing, which are the light bulbs that Mother Nature has given us. So the gas around very young stars, which are always very hot, tends to be heated so much that it glows in a similar way. And so you can see the same kind of spectrum that you would see if you were just looking at a tube in a lab on Earth. And so here we come back now to Andromeda, and you can see again sort of these reddish blobs, which now I can tell you, and you will know that they're red because this is the hot hydrogen, which is mostly red around those massive stars. And so in trying to understand the assembly history, the growth history of Andromeda, astronomers have gone and taken a spectrum of different patches of gas around young stars as a function of distance from the center of the galaxy. And so you start at the top with the ones that are furthest away, and the middle one is closer to the center, and the bottom one is very close to the center. And you'll see that these lines, so this is a hydrogen line, the red line here on the right, are changing. And these are oxygen lines, are changing relative to one another. You can also see that as you move closer to the center of the galaxy, we're seeing more background light from stars. That's why the slope of this is changing. And so we can use data like this to understand how the amount of these elements is changing as a function of a location in the galaxy. So hopefully this gives you some context for why spectrographs are so important to astronomers. And I once calculated at an observatory that I frequent that 80% of the instruments on the telescope were either purely spectrographs or capable of spectroscopy. And so oftentimes when a large telescope is working or an astronomer is taking data, they're taking spectra. And it's so that they can glean this information from all sorts of objects out in the universe, galaxies, stars, planets, etc. So I think this is a moment where I can pause and maybe see if there are any questions about spectroscopy and how we can maybe use it to understand the presence of elements in space.
Currently, we have no questions coming from YouTube right now.
Okay, perfect. All right, so when we want to apply this to more distant objects, we have a few other challenges. And so this is a schematic showing, you can use the same observatory to look at lots of galaxies, but because of the expansion of the universe, the things that are, just because of the constant light travel time, actually, things that are further away from us, we're seeing earlier back in their history, right? It takes much longer for the light to arrive from a distant object than from a closer object. And so when we see more distant objects, we're looking back in time, but it's also more challenging because just like if you took a light bulb and moved it further away, it becomes fainter and fainter. And so the objects that I look at are actually very, very far away. And so we're looking at the universe as it was 10 to 12 billion years ago. And the age of the universe is, almost 14 billion years. So we're looking at the universe when it was very young, only a fraction of its current age. And so this is another picture, not quite as nice as the picture from Hubble, where all of these, or most of these objects are galaxies. And the one that I study is this faint red blob here that you may or may not be able to see depending on the quality of your monitor. And this is because of its great distance. But if we want to study the universe at this time, basically all of the objects are very faint. So as a result, if you're interested in studying galaxies in the early universe, you need to use very large telescopes because these facilities with large mirrors, so 6 to 10 meters across, all function as a very big light bucket. You can imagine if you had an eye that big, how far you could see. And so this is actually an aerial video of the observatory that I visit in Chile, Las Campanas Observatory. And these silver domes on the highest part are the Magellan telescopes. They're identical 6.5 meter telescopes. And all of the spectrographs that I showed you before are ones that are installed on one of these two telescopes. There are older, smaller telescopes on the hills to the left. So the second challenge that I hinted at before is that not only are galaxies very far away, but the universe is expanding and it's accelerating now, its expansion. And so you are not only struggling to observe things that are very faint, but these spectroscopic features that you're interested in are also changing where they fall in wavelength. And the reason for this is essentially the Doppler effect. So you can think about a time when an ambulance was coming towards you. And as it got very close, you heard the pitch go up. And as it went away, you heard the pitch drop. So it went from high frequency to low frequency. And it's the same kind of thing. For the ambulance, the sound waves are getting stretched out. For a galaxy spectrum, the spectrum is getting stretched out. So if this is what hydrogen looks like in a nearby galaxy. In a somewhat far away galaxy, it's going to be stretched a little. And now where you might have expected to see this red line, you're actually going to be seeing light in this blue line, but you won't know that it's the blue line unless you look for this distinct pattern. And if you look at galaxies like the ones that I'm talking about, 10 billion light years away, you're seeing things where the brightest line in hydrogen is now so stretched out that you can't even see it with your eye. So we can't use those spectrographs that I showed you before because those spectrographs only operate in the visible part of the spectrum. So instead, what we have to rely on to study galaxies at this distance and at this time in the universe's history, they have to be infrared sensitive. And so this is just 3 examples of infrared sensitive spectrographs on 3 different telescopes. So this one, FIRE, the folded port infrared echelette, is on Magellan. MOSFIRE, the multi-object spectrograph for infrared exploration. We really try and contort for acronyms in astronomy, is on a large telescope in Hawaii. And this is one that I used a lot when I was doing my PhD research. And this one down here is on a European telescope that's also in Chile. And you can see that they all look very different. But they're all looking at this infrared portion of the spectrum that lets us look for these signatures of elements in these very distant galaxies. One of the challenges, however, has been that the development of infrared technology has lagged behind optical technology. And so we weren't able to do the same things at infrared wavelengths as we were at optical wavelengths until the last decade. And so, trying to understand all of these many galaxies that are very far away, we've known that they were there, but we couldn't learn a lot about them. But today we are lucky enough to be able to have very large samples. And so I'm going to show you some examples of what the real life spectra of these very distant galaxies look like. So in the bottom panel, you'll see something that kind of looks like the vertical line schematic of the spectrum. So you're seeing white patches where there's lots of light, and in between those lines, there's not as much. It's not color coded, but this is bluish, this is greenish, this is red. And in fact, these are the hydrogen lines that we showed before when we were looking at the gas in the Andromeda Galaxy. These are the same oxygen lines, but there are also lines of nitrogen and sulfur. And so we see evidence of all of these different elements in this galaxy, and we can begin to understand how much of each of these are present. But if you look at more than one galaxy, you'll see that they're all quite different. And the sort of appearance of these spectra and the shape of these lines with respect to one another are changing as you look at different objects. And just like this signals different amounts of oxygen and different amounts of hydrogen as you move to different places in the Andromeda Galaxy, this is telling us that these different galaxies are also differing in their chemical composition, the amount of elements that they have. So again, hydrogen and oxygen, nitrogen and sulfur, and it's sort of the same stacked up. In some cases, you see these sort of very interesting tilted features. This is just saying that the part of the galaxy that was up here is coming close to us, and the part of the galaxy down here is going away. So there's actually quite a lot of information to be learned using these spectra. Okay. So I said we had to wait until the last decade to begin studying samples of galaxies at this time. And to give you an idea of where we were before and where we are now, I have a little bit a little cartoon. So prior to 2012, which was when MOSFIRE was commissioned, so one of those infrared spectrographs, there were about 100 galaxies with decent spectra that would let us begin to understand the details about them. Today, we have almost 1,500. And this is actually probably excluding a couple smaller samples. We have several hundred, a little over 500 to 800, depending on how you count, galaxies where we can begin to learn about their chemical composition, so how much of each element they have, where the same degree of quality, so these were things that we could start to do it, and this is things where we could really do more detailed analysis. There were only 4. And so you see a rapid expansion in the size and quality of the samples that we have to study the universe's history at this time. Okay, so now I'm going to show some plots that are a little more scientific, but I think that you are all prepared since we've talked a little bit about all of the things that will show up in them. So this is a histogram showing the number of galaxies that have a different ratio of oxygen to hydrogen. So things here have a lot of oxygen relative to hydrogen, and things down here have very little oxygen relative to hydrogen. And what this tells an astronomer is that these galaxies are probably very young, and these galaxies are probably very old. And the reason why we know this is because when the universe, just after the Big Bang, when the universe was beginning to do more interesting things, we basically only had hydrogen and helium, a little bit of lithium. And all of the other elements have to be formed in a star. So I think you've probably heard the Carl Sagan phrase about how we're all made of stardust. And so this periodic table, rather than showing you the spectrum of each element, is showing you how much of each element is formed in different stars. So blue is what was present after the Big Bang. And then everything that is orange, yellow, green, and blue has to be formed in a star. So you'll see that oxygen entirely formed by stars, and it's formed by very massive stars. And we know that the lifetimes of massive stars are very short. And so if you were just tracking how much oxygen there is, you're basically tracking the number of stars that have been created, right? So you can sort of say this much oxygen comes from this star, and then you add up. And so you see some amount of oxygen, you divide, and you get sort of a number of stars. So you know that something with more oxygen has been around longer because it's formed more stars. Okay, so we were talking about hydrogen and we were talking about oxygen on the previous view graph, but there's a lot of other elements. And as you saw in the stellar spectrum, a lot of other elements that we can see in galaxies, in stars. And one of the ones that I want to focus on is iron. And the reason why I want to talk about iron is because, unlike oxygen, a large fraction of iron actually comes from low mass stars, which end their lives as white dwarfs. And because the lifetime of low mass stars is so much longer than that of massive stars, if you see iron, you know that you've seen a star that has lasted longer. So it forms on a different time scale than oxygen. It's much slower to arrive in a galaxy. And so now if we look instead at the ratio of oxygen to iron, so how much stuff is formed very quickly versus how much stuff is formed very slowly, we can see things that have a lot of iron relative to oxygen probably means that you are now seeing it much later, but also that all of those long-lived stars are the ones that dominated the history of the galaxy. And at the other side, you see that these things are growing quickly. And so you can learn not only about the age of a galaxy, but also how it grew. And so this is what we're beginning to do now for hundreds of galaxies 10 billion years ago, basically. Okay, so before I move on, are there any questions?
Yes, actually. Can you hear me?
Mhm.
Oh, okay.
Yes.
Let me see how to word this. You're taking the collective spectrum of a faint shaft of light
Yes.
from a distant galaxy.
Mhm.
And you're doing the evaluation that we just saw. Now, it's from the photographs I saw, it's hard to discern the orientation of that galaxy.
Mhm.
And it would strike me that if you had any particular galaxy, if you took the collective spectrum of it plain view, and compared it with the collective spectrum of it edge view, that there would be a significant difference, because there would be obscuring, on an edge view, there would be obscuring dust and stars. Is that?
That's a great question. Well, a great issue to bring up, and is related to what I was going to talk about in a moment. I should not have gone back. So you're right. Everything that I've shown so far is essentially taking all of the light from a galaxy, irrespective of its orientation, and sort of lumping it together. So we're not learning about different parts of the galaxy like we can with the Milky Way and with Andromeda. And you're right that if you look at a spiral galaxy edge on, you often miss a lot because of obscuration, not only because it's harder to see the stars behind other bright stars, but also because there's dust and you're seeing more of that dust. So we try to account for the effects of dust. This is something that we can do by looking at the pattern of certain lines that are very sensitive to dust obscuration, and we know what their intrinsic ratio should be. And so if we compare that to the ratio we see, we can try and understand how much dust there is. But this is certainly a challenge. And so ideally what you would do, even with galaxies at this very far distance, is try and look at different parts of galaxies. And it doesn't quite address this issue of orientation that you mentioned, but it gets us a little bit closer to understanding how different parts of the galaxy might differ in terms of what their spectrum looks like, and thus their elemental abundances. Does that help?
Yes. It illuminates the problem.
Yes, no, it's a big problem that we're actually hoping to address in the next decade. And I was actually just going to explain how, so it was perfect timing. So if the spectra that I was showing, as he pointed out, are all of the light from all of the stars in a galaxy, but we know from studies of nearby galaxies like Andromeda and the Milky Way that galaxies are quite complex and have different components. You have the spiral arms, you have the big ball in the center. You can see the sun is actually pretty far out in the Milky Way. What we would like to do, even for these galaxies that I've been talking about, is be able to study much smaller regions of those galaxies. But the challenge is, again, that these objects are very faint, but they're also apparently very, very small. And so you need not only the light collecting power of a very large telescope, but if you have a larger mirror, you're also actually be able to see finer detail. Your spatial resolution is better. So the part of the galaxy that you can see is much better. So this is a promotional video from the Giant Magellan Telescope Consortium showing what the Giant Magellan Telescope is. So this is going to be the next big observatory on that mountain that I showed you. It'll have an effective telescope area. You can see it's actually kind of a cloverleaf design. of over 20 meters. And there's another one called the 30-meter telescope that would be 30 meters across, and the extremely large telescope, we're not super creative, that the Europeans are building is also on order. So the next sort of big thing for ground-based astronomy is to build these giant telescopes. And so this is, letting you see detail, like you could imagine seeing detail on a coin from across the country, or seeing a candle on the moon. That's the kind of thing that we're talking about here. So these facilities are going to be the ones that let us do the kind of work that you're asking about. So the Giant Magellan Telescope is still in sort of planning and fundraising stages, although a number of the mirrors are already made and teams are already hard at work designing instruments for the facility. And in fact, they've already started building this structure on the mountain, and operations should begin at the end of this decade. So this is something that we're all very excited about. So another thing that is coming up a little more quickly is the James Webb Space Telescope that you may have heard about since it's been in the news now for quite a long time. Right now, it is scheduled to launch in late November, early December, and we're very much hoping that that doesn't slip anymore. But NASA has, NASA has made this video to try and keep us all patient, because it has been a project that has been pushed back and pushed back and pushed back for about a decade. So you'll see that the James Webb Space Telescope mirror is also very large. It's about 6.5 meters across, so much larger than Hubble, which is its predecessor. And because it also operates at infrared wavelengths, like the telescopes I was telling you about before, it will be able to see further back in the universe's history. So the James Webb Space Telescope is the next great observatory that NASA is launching. And in fact, just earlier this year, we found out which astronomers were going to be able to use it for its first year in space. And a team that I lead was actually selected to be one of those groups. So we're very excited that we're going to be able to use this telescope to study a special subset of the galaxies that I showed you that will let us make even better methods for determining how much of the elements are present in each galaxy. So we'll get an even more detailed understanding of their history. As I showed you, we're just starting this work, and so this is the next big step. And our group, the survey that we are going to run is called Chemical Evolution Constrained Using Ionized Lines in Interstellar Aurorae. So we talked about those ionized lines in interstellar aurorae. We talked about chemical evolution, but this spells out Cecilia. And this is in honor of Cecilia Payne-Gaposchkin, who received the first PhD given to a woman in astronomy in the US, and it was a transformative thesis. She talked about the chemical composition of stars, and was one of the first people to really show convincingly that, what stars were made of and how this related to our understanding of their structure. So we were very happy about this. So we are especially invested in making sure that it launches as soon as possible and without any problems. So keep your fingers crossed for us. So this brings us to the end of what I wanted to tell you today. And so to briefly recap, we talked about how astronomers use spectroscopy to determine which elements are present in galaxies, and how this chemical DNA, how this pattern teaches us about galaxies and how they relate to one another. And we talked a little bit about how we're going to be continuing this work in the future to be studying things like this, some of the most distant galaxies that we know about in the universe. So that's all that I had. Feel free if you have other questions and you don't want to ask them now to reach out to me, but I'm happy to answer any questions that people have at this time.
How difficult is it getting time to use this equipment?
It depends on which facility. So larger telescopes tend to be more expensive to build and more expensive to run. And as a result, you have larger constituencies. And so you have more people applying for time to use those telescopes. So for James Webb, I think every astronomer I knew was on a proposal to use it. And so it was one of the most competitive selection cycles in recent memory. But typically when we talk about the sort of large telescopes that give the kind of data that I was showing already, we're talking about an oversubscription rate of several. So, 2 to 5, as much time is asked for as there is. The community of astronomers is only growing. There are more and more departments at universities in the US that are beginning to have astronomy programs. And so you just see a lot of people very interested in answering these questions, which is great because there's a lot that we still don't know.
Yeah. Are there others who are doing similar projects as yours? And do they share that information, or is it yeah, you know what I mean.
That's a good question. There are other groups doing similar work. So extragalactic astronomy, so as the study of things outside of the Milky Way, is the largest sort of group of astronomers, but obviously there's a lot of stuff outside the Milky Way, so there's a lot of things to work on. What specifically I talked about today, there are probably two or three other groups in the world working on. And when we first started collecting data, that 2012 date that I showed, we definitely weren't sharing at that time. We each wanted time to do our own work, but we're actually beginning to merge samples and do joint analysis now, which I think will allow us to answer different questions than we were able to answer alone.
Do you think that the James Webb scope, that they will change the name to, you know what I mean?
Yeah, so if you're not aware, well, there's a couple of things about the name of James Webb. So typically we have not named telescopes before they were launched. So I actually don't remember what Hubble was called before it was launched. The X-ray telescope, Chandra, the X-ray Great Observatory, was called AXAF. I don't remember what that acronym stands for. There's one named after Spitzer, which was in the infrared, and that was called SIRTIF, Space Infrared Telescope Facility. And actually, it was considered bad luck to name it before it was launched. And so if you're a superstitious person, you might say that part of our trouble with James Webb is because we named it too early. But the other part of your question may relate to the fact that there has been so James Webb has a complicated history. He was very important in the history of NASA and this kind of project, but he created an environment where there was a lot of bias in NASA. And so in particular, was very dismissive of complaints of homophobia. And so there's been a push to rename the telescope, not only to address those concerns, but also to, reflect the fact that astronomy is now done by all sorts of people of, different genders, different races, from different kinds of institutions. And so, I don't know if they're going to rename it though. I don't have a great sense of what the how stiff the bureaucratic channel is there.
Yeah. Just one last question for me. Have you had a chance to visit Chile and Hawaii and these, or, yes, you have.
Yeah. So, I was talking to some folks before the talk. I'm what people would consider a classically trained observer in the sense that the way I was trained is not so dissimilar from the way that someone like Hubble might have been trained. You know you're interested in a topic and you go out and look at what there is, and you don't necessarily know what you're going to find. So it's not exactly the scientific method that you were taught in school, where there's a hypothesis and whatever. So actually, the reason I became an astronomer is because I love going to the telescope so much. The first telescope I observed at was at Kitt Peak National Observatory in southern Arizona. And then when I was a graduate student at Caltech, I went out to Hawaii pretty frequently to use the Keck telescopes. And then as a Carnegie Princeton Fellow, so my current position, I go down to Chile quite a bit. Not recently, of course. COVID has accelerated plans to make observing remotely possible. And I think that you'll begin to see a decline in the number of astronomers who go to the facilities that they use.
I see.
All right, we do have a few YouTube questions that came in. First one, can you distinguish the spectra of different oxidation states?
Okay. So what we can tell is whether a line is coming from a different ion of the same atom. So if you think about our model of an atom with having a nucleus of protons and neutrons, and you have some number of electrons equivalent to the number of protons in some probabilistic field around the nucleus, you can be stripping off those electrons because of interactions with other atoms. And those ions actually have subtly different spectral fingerprints, or those patterns that I was talking about. So we actually can tell. The oxygen lines that I pointed out in the spectra that I was showing are actually doubly ionized oxygen. So 2 electrons have been taken away from that oxygen, those oxygen atoms.
Okay, next question is, I thought that it's the wavelength that gets stretched out while the spectral lines change color, but the elements can still be identified by the pattern. Is that wrong?
No, that's correct. If I didn't explain that very clearly, that is exactly what's happening. The spectrum is getting stretched, and so the pattern of lines stays the same. I think what I meant when I was talking about that is that if you can't see the full pattern, sometimes you can get confused because you see the line at some observed wavelength, which is not the wavelength that it corresponds to in the unshifted case. And so ideally you see multiple lines so you can look exactly for that pattern. That's correct.
Next question is, what is the process in the stars which forms the elements?
That's a great question, and still for some elements a very active area of research. So I guess the most basic answer is nucleosynthesis, which I guess is sort of a roundabout way of saying that it forms different nuclei, which occurs because in the centers of stars, they're under immense pressure because of all of the material of the star. And in order to hold up that material, you actually have to be generating opposing pressure. And that comes from energy generated by merging nuclei together. So they're exothermic reactions. And so by converting lower number elements into higher number elements, you're actually providing the energy and the support that the star needs to stay. And so that's how, things like carbon and oxygen can be formed in like white dwarfs, so solar type stars. But actually a lot of elements are formed in explosive nucleosynthesis. So they're actually formed when the star explodes because of the sort of energy and the flux of various atomic particles that are released. And so not only do you see elements formed in those kinds of explosions, but actually, unless a star explodes, you'd never see any of the elements that it's made back in the galaxy. So it's really the explosions that are the sort of the critical part of that cycle.
Will it be possible to isolate globulars from galactic arms for spectral analysis of distant galaxies?
Yes, to a point. So if you are an aficionado of astronomy, you will know that globular clusters, particularly those in the extended halo, tend to look very different in composition from stars in the arms, like the area near the sun. And we cannot currently distinguish those for things beyond a few megaparsecs. But with things like the giant Magellan Telescope, we are hoping to be able to sort of distinguish those galactic components, including globular clusters, from other things. That's not going to be possible for the kinds of galaxies I study, but we'll be able to push that out further than we can do now.
Is Hubble telescope still hard to get time on?
Yes, it is actually. I don't use Hubble very much myself, but I have a number of collaborators who do, and we get more rejections than we get acceptances. It's still oversubscribed by a factor of several, and in particular, right now, because there's eventually Hubble will no longer be operational. I don't know if you followed the news this summer where there was an issue, and so it was actually out of commission for a little while. And because Hubble is currently our only opportunity to observe ultraviolet light from objects in space, you can't actually observe those wavelengths because it's absorbed by the atmosphere. So we have to do it from above the atmosphere, but no other telescope, including James Webb, actually operates at those wavelengths. Most Hubble time is going to ultraviolet observations. And so if you want to do something that's not at ultraviolet wavelengths, you have an even harder time convincing them to let you use the telescope.
Are scientific acronyms made by grad students or special teams of publicity agents?
I think it depends on the acronym. I have been involved in making more than one acronym, including Cecilia. But things like GMT, TMT, maybe the more boring ones are usually made by higher level committees. You'll see some quite tortured ones. There's one called smudges. What does smudges stand for? And it's like you're pulling letters out of the middle of words, and it's to describe the study of sort of faint, fuzzy galaxies. So it's quite apropos, but not necessarily what one thinks about when one thinks acronym.
And that's the final question.
Okay, well, that's cool. We went far in a field. I loved it.
All right. Since we don't have any other question, or John, do you have another question?
No, I just wanted to thank Allison very, very much for presenting. Next time you can visit us. You're close enough, and an invitation to come, but the situation with COVID.
Yes,
So,
it's still, I'm here in my office, but we have to wear our masks in the hallway.
Yeah.
And so things are still very strange. But hopefully I will get to, attend something like this in person.
That's good. We'll be in touch.
All right. Well, thank you everyone for your time.
And then the live stream right now, and you can still hold on.